Right now, sitting at the bottom of the Pacific Ocean in just absolute crushing, freezing pitch blackness,
Mhm.
there are, there are 500 billion tons of rocks that look exactly like blackened potatoes.
They really do. It's a perfect visual.
Right. And these potatoes, just kind of resting quietly in the mud, are currently at the center of this, like, trillion-dollar geopolitical standoff.
Which is wild to think about.
It is. Because the next electric vehicle you buy, or, the battery in the laptop you're literally using right now, depends entirely on what is trapped inside those rocks.
Exactly.
So, okay, let's unpack this. Because to truly understand what's happening at the bottom of the sea, we have to connect some seemingly impossible dots for this deep dive.
We do. We're covering a lot of ground today.
Yeah, we are going to trace a line from those dark abyssal plains in the Indian Ocean, straight up to the dirt under your front lawn, and all the way back to a 2-billion-year-old crater in West Africa.
I know it sounds like an incredibly disparate set of locations, but there is actually this single geochemical thread tying them all together.
And it's all based on the sources we've been reviewing, right?
Yeah, we are looking at a fundamentally misunderstood element that essentially bridges oceanography, microbiology, and the actual paleoclimatic history of the Earth.
And usually when we think about the history of the planet, or even just like the chemistry of life, we picture this grand stage. You have the superstar actors taking all the credit.
Right, like oxygen giving us breath, carbon building our bodies.
Exactly. Or iron forming the molten core of the Earth. It's a very dramatic, very visible cast of characters. But when you synthesize the research coming out of marine biology and geochemistry right now, you realize there's this quiet stagehand lurking in the background.
A very busy stagehand.
Yeah, a stagehand pulling the ropes, changing the lighting, setting the entire scene for those superstars to do their thing. And without this stagehand, the whole production just completely falls apart.
And in the elemental world, that stagehand is manganese.
Manganese.
Right. It rarely gets the headlines, but functionally, it is this unsung hero that regulates massive planetary systems.
Which is just wild to me, because to most of us, manganese sounds like a typo of magnesium.
It does, yeah. They get confused all the time.
But if you are wondering why you should care about this totally unassuming metal, it's because the food you eat grows in soils that are chemically regulated by it. And the very history of Earth taking its first breath of oxygen is written entirely in it.
It really is the thread connecting our technological future to our deep biological past.
So we are going to start this journey by heading down to the absolute bottom of the world, the deep ocean floor.
Because that is where we find the most visually striking and currently, like you said, the most contested form of this element.
The potatoes.
The potatoes, yes. Polymetallic manganese, nodules, and crusts. To understand the stakes of the modern green transition, you really have to look down, way down into the abyssal plains.
And the human realization that these things even exist actually starts way back in 1868.
Yeah, it's older than people think.
Oceanographers were up in the Kara Sea in the Arctic Ocean off the coast of Siberia, and they were essentially just dragging nets blindly along the bottom of the sea to see what they could pull up.
As you did in the 19th century.
Right, just grabbing whatever. But they really got famous a few years later during the HMS Challenger expedition. Between 1872 and 1876, they were pulling up these weird black knobby concretions.
And the scientific descriptor for that specific knobby texture is botryoidal.
Botryoidal. That is a great word.
It's a fun one. It derives from the Greek word for a bunch of grapes.
Oh, okay.
Yeah, so when minerals precipitate out of water extremely slowly, they often form these rounded, bulbous clusters instead of like sharp geometric crystals.
So they look exactly like blackened, slightly bumpy potatoes. Or grapes, I guess.
Yeah, usually about 3 to 10 centimeters in diameter, so literally the size of a hen's egg or a small baking potato.
But the scale, the sheer volume of these things sitting down there is what completely breaks my brain.
The numbers are staggering. The estimates suggest there are 500 billion tons of these nodules.
500 billion tons.
Yeah. And if you look at the mapping data from deep-sea submersibles, there are vast regions where they aren't just scattered randomly. They are so densely packed that they are physically touching one another.
Like a cobblestone street.
Exactly, creating this endless cobblestone street that covers up to 70% of the seabed in those specific areas.
70%. Just a paved road of metal grapes sitting in the dark. And we find them in these incredibly specific, massive fields.
Right.
The most famous one, the one getting all the attention right now, is the Clarion-Clipperton Zone, or the CCZ.
That's the big one.
Yeah, this vast stretch of the Pacific Ocean, basically midway between Hawaii and Mexico. And it's sitting at depths of 4,000 to 6,000 meters. But marine geologists are finding major sites globally, right?
Oh, absolutely. There's the Penrhyn Basin near the Cook Islands, the Peru Basin, and the Indian Ocean Nodule Field.
Okay, so they're everywhere.
They are, though it is really crucial to understand that manganese doesn't exclusively form as loose potatoes resting on soft sediment.
Okay, what else does it do?
Well, the oceanographic studies mapping out the Perth Abyssal Plain, specifically the Dirk-Hartog Ridge in the eastern Indian Ocean, they provide a vital contrast.
Right.
In that environment, we see hydrogenous, cobalt-rich ferromanganese crusts.
Okay, crusts instead of nodules. What is the physical difference down there?
Well, instead of precipitating around a tiny, loose core in the mud, these crusts precipitate directly onto towering hard rock surfaces.
Like underwater mountains.
Exactly. They coat the steep sides of underwater mountains and ridges. And the substrate they grow on, the underlying rock itself, is highly altered, phosphatized, and zeolitized basalt.
Okay, let's pause there for a second, because phosphatized and zeolitized basalt is quite a mouthful.
It is a bit dense, yeah.
What is actually happening to the side of that underwater mountain?
So imagine a volcanic eruption underwater millions of years ago. That lava cools rapidly into solid basalt rock. Over immense stretches of time, the corrosive nature of seawater, physically and chemically, breaks that solid rock down. The volcanic glass alters into minerals called zeolites.
Zeolites?
Yeah, which have this porous, honeycomb-like microscopic structure. At the same time, phosphorus, which largely comes from the decaying remains of marine organisms just kind of drifting down from the surface, that phosphorus reacts with the degrading rock to form phosphate mineral.
Oh, wow. So the mountain is essentially rotting into this highly reactive, porous chemical sponge.
That is exactly it. And it is onto that degraded, spongy surface that the dense, metallic manganese crust forms.
It's like the mountain is rusting, but it's rusting with some of the rarest metals on Earth.
Precisely.
Now, whether we are talking about the loose nodules in the Pacific or these thick crusts in the Indian Ocean, the part of this that I really struggle to even conceptualize is the time frame.
Time is the crazy part here.
Because it's not like a volcanic eruption where lava cools into a rock over a week.
Far from it. This is arguably one of the slowest geological phenomena known to science. It really tests our fundamental conception of time.
How slow are we talking?
These formations grow at a rate of roughly 1 centimeter every few million years.
Wait, what?
Yeah. The global average is somewhere between 10 and 20 millimeters per million years.
1 centimeter. A million years.
That's right.
So if you were holding a 10-centimeter nodule, like a rock the size of a baking potato, you're holding something that could be 10 million years old.
Easily, yes.
The very center of that rock started forming before the first human ancestors even walked upright on land.
It's profound when you really hold that in your head, and the mechanism behind that excruciatingly slow growth is fascinating too.
How does it even start?
It requires a nucleus. There must be a piece of debris sitting on the seafloor to kick it off.
Like what?
Like a shark tooth, a fragment of an older broken nodule, a tiny bit of sunken biogenic matter, maybe just a stray rock fragment.
Just a piece of trash, basically.
Exactly. And then the manganese and iron that are naturally dissolved in the seawater, in unimaginably tiny trace amounts, mind you, they slowly begin to precipitate.
So they just drop out of the water.
Right. They drop out of the water and crystallize around this core, layer by microscopic layer.
So they are basically geological pearls.
That's a great way to think about it. Like
a grain of sand gets into an oyster, and the oyster coats it over years to make a pearl. But here, a megalodon tooth hits the ocean floor, and the ocean coats it over millions of years to make a massive manganese nodule.
The pearl analogy works incredibly well visually, but chemically, how that coating happens is highly dependent on exactly which part of the ocean environment the rock is touching.
Okay, meaning top versus bottom.
Yeah. Marine geologists categorize this growth into 2 distinct processes, hydrogenetic and diagenetic.
And the distinction between those two is critical, right? Because the way it grows dictates exactly what kinds of valuable metals get trapped inside.
Yeah, absolutely.
So how does a hydrogenetic growth work?
Well, hydrogenetic growth happens from the top down. So it's the direct precipitation of metals from the overlying oxygen-rich seawater.
The open water.
Exactly, what we call the oxic water column. And because the metal concentrations dissolved in that open ocean water are incredibly, incredibly low, this is the slower form of growth.
Slower than a centimeter a million years.
Yeah, we are talking 2 to 5 millimeters per million years for this part. And this top-down process primarily forms a mineral structure known as vernadite.
Okay, so top down, extremely slow, pulling from the open water.
Yeah.
What makes this vernadite special?
Hydrogenetic vernadite is characterized by a very high iron and cobalt content. However, it has a lower overall ratio of manganese to iron,
How low?
specifically a ratio of less than 2.5 to 1.
Got it. So that is the top half of the potato facing the open water. What about the bottom half that's sitting in the mud? That's the diagenetic growth.
Exactly. Diagenetic growth happens from the bottom up. It precipitates from the pore water.
Pore water.
Yeah, that's the water physically trapped within the microscopic spaces of the soft sediment the nodule is resting on.
Oh, yeah.
And this buried water has vastly different chemical properties than the open ocean above it. It's suboxic.
Meaning low oxygen.
Right. It's been starved of oxygen by microbial activity in the mud.
And because it's starved of oxygen, the chemistry flips.
It does. The lower oxygen environment allows for slightly faster growth.
Fast being, what, 10 millimeters?
Yeah, around 10 millimeters per million years. It also forms a completely different mineral structure called bucerite.
Bucerite, okay.
And diagenetic bucerite is heavily enriched in manganese, nickel, and copper. The manganese to iron ratio shoots way up from 2.5 to sometimes over 30.
Wow. So the top of the rock is grabbing cobalt from the open ocean, and the bottom of the rock is pulling nickel and copper from the mud.
Yes, and what is really beautiful about examining a cross-section of a nodule is that they are almost always hybrids.
Meaning they have both.
Yeah, they have diagenetic layers on the bottom and hydrogenetic layers on top. But over millions of years, deep-sea creatures or strong abyssal currents might slowly roll the nodule over.
Oh, so it flips.
It flips. And when it flips, the growth patterns reverse.
That is so cool.
So the old top now sits in the suboxic mud and starts growing bucerite, while the old bottom is exposed to the oxic water and starts growing vernadite. The alternating rings inside the nodule create a literal historical record of its physical position on the seafloor over deep geological time.
That is incredible. But, it also leads me to a major point of pushback here.
Sure.
If these things take millions of years to grow a single centimeter, aren't we just completely kidding ourselves when we talk about them as a resource?
That's a very valid question.
Because I hear mining executives talk about harvesting these nodules like there are potatoes in a field. But a potato grows back next season. If you pick up a manganese nodule, you are permanently removing a 10-million-year-old habitat. I mean, it is not coming back.
You are hitting on the fundamental tension of the entire deep-sea mining debate right there. From a geological timescale, sure, they are dynamic, growing entities. But from a human economic timescale, they are absolutely static, non-renewable resources.
They're gone.
Yeah, once that specific microhabitat is removed, it is gone permanently for all human intents and purposes.
Which makes the rush to secure them so intense. And to really understand why humans want to pull these ancient formations off the seafloor so badly, we have to zoom way, way in.
We do. We have to go from the vastness of the abyssal plain right down to the atomic level.
Right. Why are these specific rocks packed with so many incredibly valuable elements? Why is there so much cobalt and nickel locked inside?
The answer lies in the physical architecture of the oxide molecules themselves.
The architecture.
Yes. Manganese oxides don't just form solid, impenetrable blocks of matter. They build highly intricate crystalline structures that contain microscopic voids.
Voids, like empty spaces.
Exactly. And it is the precise shape and charge of those voids that make them so unimaginably valuable to modern technology.
Okay, so when geochemists look at these under electron microscopes, they see a few distinct structural shapes.
They do.
There are layered or pseudo-layered structures like the vernadite we just talked about, or another one called B.O.O.G. Then there are hybrid structures like lithiophyllite.
Yeah.
And finally, you have tunnel structures like todorokite and cryptomeline.
You've got it. And within all of these varied crystalline geometries, there is a recurring phenomenon called octahedral vacancies.
Octahedral vacancies, which sounds like an overpriced apartment building in a major city.
It really does.
But what is an octahedral vacancy physically?
Well, at the atomic level, the manganese atoms and the oxygen atoms bond together to form a lattice, a repeating geometric scaffolding.
Okay, scaffolding.
In this case, they form an octahedral lattice, which you can picture as an 8-sided, diamond-like shape. But in nature, this scaffolding is almost never perfect.
It has flaws.
Exactly. There are missing manganese atoms in the lattice. These literal empty spaces in the atomic structure are the vacancies.
Okay, so there is a hole in the scaffolding. Why does that matter?
Because a missing atom leaves behind an unbalanced electrical charge.
Oh, I see.
The empty space creates a localized negative charge within the crystal, and the universe abhors an unbalanced charge. So the mineral actively attempts to balance itself by pulling in positively charged metal ions from the surrounding seawater to fill the void.
Ah. So it is acting like a molecular sponge, or really a highly specific molecular hotel.
The hotel analogy is excellent, actually, because it explains the mechanisms of contiguities exchange and surface complexation perfectly.
Right, let's explore that because I think it's so helpful. Think of the different crystal structures of these manganese oxides as different types of molecular hotels.
Okay.
That layered vernadite, the one growing on the top of the nodule, is like a sprawling, open-air beach resort. The atomic layers are stacked like sheets of paper with wide gaps between them.
Yes.
And because the gaps are wide, it is really easy for elemental guests like dissolved cobalt or nickel in the seawater to wander in off the beach, feel that negative charge, check into one of those octahedral vacancies, and just stay there. It is highly reactive and accessible.
That's a perfect way to visualize it. And by contrast, the tunnel structured to dorkite is much more rigid. It is like an exclusive, heavily fortified VIP suite.
Very strict hotel.
Very strict. The atoms form long, narrow, rigid tunnels. Because the entrances are fixed in size, only specifically sized elemental guest signs with the exact matching ionic radius and charge can physically fit through the doors to check in.
So they literally measure you at the door.
Basically, yeah. But once those correctly sized metals get inside those tunnels, they are locked in tightly. The physical architecture dictates the chemical trapping.
So depending on which hotel is built, different metals get trapped.
Yeah.
And we see incredibly specific examples of this trapping in the real world.
We absolutely do.
Let's go back to the Dirk-Hartog Ridge crusts in the Indian Ocean, those thick pavements on the sides of the underwater mountains.
When researchers ran microanalyses on those specific crusts, they could see exactly who was checking into which hotel.
What did they find?
They found that the most abundant and economically valuable base metals, the nickel, the copper, and the cobalt, were almost exclusively found inside the low crystalline asbelane and vernadite structures.
So they were chilling in the sprawling layered beach resorts.
Precisely. But that same study found something profoundly surprising regarding the rare earth elements, or REs.
Okay, the Aureus.
Yeah, we desperately need elements like neodymium and dysprosium for modern technology, particularly for the permanent magnets in wind turbines and EV motors.
Right, the stuff driving the green transition.
Exactly. You might assume the massive manganese hotel is trapping those too, but it isn't.
Wait, really?
Yeah, the highest concentrations of REs in these specific crust samples aren't actually in the manganese oxides at all.
Wait, if they aren't in the manganese, where are they?
They are heavily concentrated in the associated minerals at the border zone,
The border zone.
right where the thick manganese crust meets the rotting, altering basalt mountain underneath it. Remember how we discussed the basalt altering into phosphates and zeolites?
The chemical sponge.
Yes, the chemical sponge. The calcium hydroxyapatite, which is a phosphate mineral, and the zeolites, like naphthalipsite, act as the primary traps for the rare earth elements.
Oh, wow.
This tells us that the formation of these valuable deep-sea deposits isn't just a simple precipitation of manganese out of the water. It is a highly complex, multi-stage, symbiotic interaction.
It's a whole ecosystem of minerals.
Exactly. The underlying mountain degrades, forming phosphates and zeolites which trap the REEs from the deep ocean currents, while the manganese and iron precipitate on top of them, acting as the sponge for the cobalt, nickel, and copper.
And what is wild to me is that this exact same molecular hotel business isn't just some exotic phenomenon happening under thousands of meters of crushing ocean pressure.
No, not at all.
It is happening in the dirt. If you go to a forest right now and dig, terrestrial trapping works using the exact same atomic physics.
The geochemical principles are universal. When soil scientists analyze terrestrial soils, they frequently find iron-manganese soil nodules.
So soil potatoes.
Soil potatoes, exactly. They look like tiny rust-colored pebbles in the dirt.
Mm-hmm.
But high-resolution electron imaging reveals that the iron and the manganese in those pebbles don't actually mix evenly.
They don't.
No, they segregate. They form separate, distinct microdomains within the same tiny nodule.
So they build their hotels on different sides of the street.
They do, and they cater to entirely different clientele based on their specific vacancies and charges. The manganese oxides in the soil act as the exclusive carrying phase for heavy metals.
Okay, give me an example.
Well, for instance, if there is nickel in the soil water, it is almost entirely associated with the hybrid-structured lithiophyllite. Barium is overwhelmingly drawn to the manganese as well. Meanwhile, zinc might be selectively trapped by the layered burnasite.
And what about the iron?
The iron oxides in that very same nodule, sitting just millimeters away, ignore the nickel entirely and instead trap completely different elements like vanadium or arsenic.
That is just, it's an incredibly specialized sorting mechanism. And it's happening completely blindly, atomically, in both the mud under our feet and in the pitch black of the deep sea.
It's nature working at the molecular level.
But because these molecular hotels in the deep ocean are currently fully booked with the exact suite of metals we need, the cobalt, the nickel, the copper, we are facing a massive planetary-scale dilemma.
We are at a critical inflection point. A massive industrial rush is underway to strip these nodules from the ocean floor to feed the modern green technology economy.
Which creates a severe environmental paradox.
He really does.
I mean, we absolutely need these metals to transition away from fossil fuels. If we want to build billions of batteries for electric cars and grid-scale storage for solar panels, we need cobalt and nickel. But to get them, we might have to inflict unparalleled destruction on the deep sea. Let's look at the raw numbers here, because they're important. The Clarion-Clipperton Zone in the Pacific alone holds an estimated 21 billion tons of these nodules.
And locked within those 21 billion tons is an estimated 44 million tons of elemental cobalt.
That's a huge number.
To put that staggering number in perspective, 44 million tons is roughly 3 times the known economically viable cobalt reserves on all of Earth's land masses combined.
3 times the land reserves.
Yes.
Sitting right there on the surface of the mud. It's no wonder the investment is just huge. I mean, since the 1960s and 70s, multinational consortia have been quietly dumping hundreds of millions of dollars into identifying these deposits, mapping them, and developing the robotic technology to get them.
It's been a long time coming.
And now you have private companies, like the Metals Company, alongside various nation-states, aggressively pushing the International Seabed Authority, the ISA, which is a UN-affiliated body, to finalize the mining codes. They want the green light to start commercial extraction immediately.
The digital and energy transition is creating an exponential demand curve for these specific battery metals. The geopolitical and financial pressure to open this new deep-sea frontier is immense.
And the mechanics of how they actually plan to mine it, go back to the potato analogy, but on an industrial scale.
Right.
The proposed operations involve sending massive, remote-controlled seabed tractors machines, the size of houses, down to the abyssal plain.
Huge machines.
Yeah, and these tractors will crawl along the soft mud, essentially scraping the top 10 to 15 centimeters of the seabed. They use massive hydraulic pumps to suck up the sediment, separate out the heavy nodules inside the machine, and then pump the metallic ore up a riser pipe several miles long to a massive processing ship floating on the surface. It is basically strip mining in the dark.
And when evaluating this, it is vital to impartially present the ecological stakes that marine biologists and deep-sea ecologists are raising. The environmental risk assessments are sounding profound alarms about the potential for irreversible harm.
Right. What are they most worried about?
Well, the abyssal plain is largely an endless expanse of incredibly fine, soft mud. In these regions, the millions of years old nodules are often the only hard substrate available for hundreds of miles in any direction.
So they are the coral reefs of the abyss.
Ecologically, yes, that's exactly what they are. Entire ecosystems of bizarre, highly adapted benthic creatures rely entirely on the hard surface of the nodules.
What kind of creatures?
You have xenophytophores, which are giant single-celled organisms that build delicate structures on the rocks. You have incredibly slow-growing stalk sponges. You have specialized microbial mats and all the scavenging organisms that feed on them.
And they can't live in the mud.
No, because the mud is too soft to anchor to, they need the rock. If you vacuum up the nodules, you completely remove the foundational architecture of the habitat.
And we actually have a terrifyingly clear picture of what that looks like long-term, thanks to an experiment called the Discal study.
The Discal study is a cornerstone piece of evidence in marine biology.
When was this?
In 1989, a team of German researchers went to the Peru Basin and deliberately plowed an area of the seafloor to simulate the physical disturbance of a mining tractor.
Did they take the nodules?
They didn't even extract them. They simply churned them under the soft sediment so they were no longer exposed on the surface.
And then they waited.
Yes.
And they went back 26 years later to see how the ecosystem bounced back.
Yes. 26 years later, they sent cameras down. The plow tracks looked almost as fresh as the day they were made. They
Wow.
were practically frozen in time, like footprints on the moon. The tracks were completely devoid of nodules on the surface, and crucially, there was almost zero biological recovery.
Not all.
The stocked sponges hadn't returned, the microbial functions had flatlined, the faunal communities were just gone. The ecosystem was unable to repair itself.
Because again, 26 years is absolutely nothing to an environment that measures time in millimeters per million years.
Exactly.
The deep sea simply doesn't have the biological fast-twitch healing that a rainforest or a shallow reef has. And it is not just the physical removal of the hard rocks that causes damage. The impact reports outline 3 distinct types of catastrophic pollution this mining will generate.
Right. There are secondary effects.
First, you have the sediment plumes.
Right. When a tractor the size of a building scrapes the seabed, it kicks up a massive cloud of incredibly fine silt. Furthermore, when the surface ship receives the nodules, it has to separate them from the mud, and it pumps all that excess water and fine sediment back down into the water column.
That's a lot of mud.
It is. And because these particles are microscopic, Stokes' law dictates that they don't just settle immediately back to the bottom. They can remain suspended and be carried by slow deep-sea currents for tens or even hundreds of miles.
And that roaming dust storm essentially chokes the life out of the surrounding areas, right?
Yeah. Yes. Deep-sea filter feeders, which are adapted to crystal clear water, get their delicate feeding apparatus completely clogged by the silt. It suffocates them over vast swaths of the ocean that weren't even actively mined.
That's awful. And the second major impact is noise pollution.
Right. The deep sea is naturally a place of near absolute silence. It is a highly specialized acoustic environment.
So they use sound a lot.
Countless marine animals, from deep-diving whales to benthic crustaceans, rely on subtle sound waves for communication, navigation, and finding prey. The roar of massive hydraulic pumps, the grinding treads of the seabed tractors, and the low-frequency thrum of the surface ship's dynamic positioning propellers will completely mask animal communication over huge acoustic footprints.
And finally, light pollution.
Yes, light.
You are introducing brilliant, intense industrial floodlights into a world that has been pitch black for billions of years.
It's a huge shock to the system.
The creatures down there either have no eyes, or they have evolved incredibly sensitive optics to detect the faintest hints of bioluminescence. You are either going to blindly attract organisms into the grinding machinery or literally blind the creatures that rely on absolute darkness to survive.
As the pressure mounts, the mitigation strategies proposed by the mining consortia to address these impacts are, well, they're challenging.
Yeah, challenging is a very diplomatic word for it.
Engineers are looking at making the rovers lighter to reduce the deep compaction of the sediment. There are logistical proposals to mine in narrow strips, intentionally leaving unmined tracks adjacent to the stripped areas.
Hoping that works as a backup.
The theory is that these untouched strips will serve as biological reservoirs, allowing organisms to slowly repopulate the disturbed zones over time.
But the wild one, the absolute wildest mitigation idea I saw in this research, is the idea of dropping manufactured replacement nodules back into the ocean.
That is definitely the most controversial.
Taking synthetic rocks or concrete, casting them into the deep to act as artificial hard substrates to replace the millions of years of natural growth we just sucked up in a pipe.
It perfectly highlights the desperation to find a technological compromise between raw resource extraction and baseline habitat preservation.
But I have to ask, if you look at the market, tech giants like Samsung, BMW, and Google are already coming out and publicly pledging not to use ocean-mined metals in their supply chains due to the ecological concerns.
That's true. There's significant corporate pushback.
So is the economic argument for this destruction actually sound? Or are we risking the absolute bottom of the ocean, one of the most pristine wildernesses left on Earth, for a temporary battery boom that market forces might render obsolete in a decade anyway?
That is the multi-billion-dollar geopolitical question facing the ISA right now. The economic modeling relies entirely on a sustained, exponentially increasing demand for cobalt and nickel.
But that demand could change.
Rapidly. Battery chemistry is evolving incredibly fast. If the global market shifts heavily toward lithium iron phosphate batteries, which don't use cobalt or nickel, or if terrestrial recycling of existing batteries becomes hyper-efficient, well, The financial incentive to incur the astronomical costs and environmental risks of deep-sea mining could completely collapse.
Interesting.
However, right now, the strategic desire of nations to secure resource independence outside of traditional terrestrial supply chains is keeping the momentum moving forward.
Okay, we've been sitting at the bottom of the ocean for a while, surrounded by heavy machinery and giant single-celled organisms. Let's come up for air.
Good idea.
Let's take the molecular hotel concept and move from the ocean floor to the forest floor. Because while the deep sea grabs all the geopolitical headlines, you don't actually need a billion-dollar submarine to find manganese nodules.
You really don't.
They're doing critical hyperdynamic work right under your lawn.
Terrestrial manganese oxidogenesis is an entirely different yet equally fascinating theater of operations.
Where do we find them?
We see these terrestrial nodules forming in a variety of specific soil horizons globally. You'll find them in ultisols, which are highly weathered, red clay soils often found in humid areas. You see them in vertisols, which are expansive clay soils that crack deeply during dry seasons. And in alphasols, the classic fertile forest soils.
But the driver of the formation in these soils is totally different than the ocean, right?
Completely different.
In the deep sea, it's mostly this slow, abiotic chemical precipitation out of the seawater. It's just chemistry and time. In the soil, manganese oxidogenesis is heavily driven by biology, by living microbes actively building the rocks.
Specifically by complex communities of fungi and bacteria. A prime example highlighted extensively in soil microbiology is the bacterium metallogenium.
And they work fast.
Oh, the speed at which these biological actors operate is staggering compared to the marine environment.
Yeah, we are talking about growth rates measured in days instead of millions of years. And the studies mapping out the Russian plain really show how this specific ecosystem dictates the chemistry.
Right, the geography plays a huge role.
They looked at different soil zones across Russia and found that the environment completely changes the types of manganese minerals present.
Yes, the biogeography of manganese is distinct. In the northern forest and taiga soils, which are typically more acidic, podzolic soils, they found fewer varieties of manganese minerals.
Mostly just the basics.
It was mostly vernadite, along with some tellurite and cryptomaline. But when they moved south and looked at the steppe and forest-steppe soils, the rich, deep grasslands, they found a much richer assemblage of minerals.
What else showed up?
They saw the addition of bernicite and haussmannite.
Because the richer, less acidic soil of the steppe supports a completely different, more robust microbial community, which in turn drives a more diverse, complex manganese chemistry.
Exactly. The microbes are the architects, and the actual biochemical mechanism by which these microbes build the manganese oxides is just a marvel of evolutionary biology.
How do they actually do it?
Well, these microbes are essentially breathing in the soil, utilizing oxygen to metabolize nutrients. However, a natural byproduct of their incomplete oxygen reduction is the generation of hydrogen peroxide.
Wait, hydrogen peroxide? Literally the exact same stuff you pour on a cut to make it fizz and kill bacteria?
The very same.
That's wild.
Hydrogen peroxide is an incredibly powerful oxidizing agent. It wants to steal electrons. The microbes excrete this hydrogen peroxide, and they use it to actively oxidize soluble manganese too.
Which is floating freely, right?
Right, dissolved in the microscopic water droplets in the soil. They oxidize that into solid manganese-4.
So the microbe essentially weaponizes hydrogen peroxide to strip electrons off the dissolved manganese. And boom, the manganese becomes insoluble and precipitates into a solid mineral structure.
Exactly. It crystallizes into the lattice structures we discussed. And lab tests confirm that this biogenic vernadite can form in as little as 3 days.
3 days.
3 days compared to the millions of years it takes to build a vernadite layer in the abyss.
And if you are listening to this and wondering why we care about microbes building tiny rust pebbles in a forest in Russia, here is why it matters to you.
It's crucial for the ecosystem.
Because once those microbes build the manganese oxide hotel in the dirt, that mineral doesn't just sit there like a dead rock. It becomes a highly active, aggressive participant in the ecosystem. It acts as a massive chemical catalyst.
It plays a profound, indispensable role in the terrestrial carbon cycle, specifically in the creation of humus.
Right. Think about what happens when autumn comes. Plants die, leaves fall to the forest floor, and they begin to break down. Fungi and bacteria attack them, and the leaves decompose into these smaller organic compounds called phenolic acids.
Things with names like vanillic acid, syringic acid, and N-hydroxybenzoic acid.
Right, these chemical fragments.
These are relatively simple, fragmented organic molecules resulting from the initial decay of lignin and cellulose. But if they just stayed as simple acids, the soil wouldn't be fertile.
Something else has to happen.
For the soil to become truly capable of supporting complex plant life, these simple molecules need to be polymerized. They need to be chemically linked together into massive, highly complex, dark, nutrient-rich, organic webs.
And a complex web is what we call humus.
Exactly.
And researchers ran a brilliant experiment testing exactly how this happens. They took these simple phenolic acids from dead leaves and put them in contact with different common soil minerals to see what would trigger the polymerization.
It was a very telling experiment.
They tested aluminum oxides, nothing happened. They tested silicon oxides, nothing. Even iron oxides, which are everywhere in soil, were pretty sluggish and ineffective. But when they introduced the manganese oxides,
A completely different story.
the reaction was violent and immediate. The manganese violently oxidized the phenolic acids. Within a short time, it oxidized 80% of them, rapidly forcing them to bond and polymerize into that complex, dark humus.
The manganese oxide acts as an insatiable electron acceptor.
Okay, an electron acceptor.
By pulling electrons away from the phenolic acids, it destabilizes them and forces them to form new chemical bonds with each other. It facilitates the literal chemical reactions that turn dead, decaying leaves into life-giving, fertile soil.
Without it, we'd be in trouble.
Without this manganese catalyst, the carbon cycle in the soil would bottleneck. Forests would drown in simple, unreactive decay.
So to really visualize what this element is doing under our lawns, I like to think of the terrestrial manganese nodule as a microscopic bouncer and a bartender working at a club.
A bouncer and a bartender. Let's explore the mechanics of that analogy because it's interesting.
Okay, so it acts as a bouncer because, as we discussed with the molecular hotels, it locks up toxic heavy metals if vacancies have a negative charge.
Right.
If a dangerous positively charged atom of lead or nickel is floating through the soil water threatening to be absorbed by a plant root, the manganese nodule grabs it.
It traps it.
Yeah, it pulls the lead into its atomic structure and traps it, effectively bouncing the toxic element out of the active biological ecosystem so it can't poison the forest.
That is a highly accurate description of excursion sequestration. It provides a vital ecological buffering service.
But at the exact same time, it's also the bartender.
Okay, how is it the bartender?
It is violently grabbing these simple, unlinked organic acids from the dead leaves, stripping their electrons, shaking them together, and forcing them to react until they polymerize into a massive, rich, complex humus cocktail that feeds the entire forest. It bounces the toxins and mixes the nutrients.
That is a highly effective, memorable way to visualize its dual role.
I thought so.
However, we must also acknowledge that this powerful bartender has a very dark side.
Uh-oh.
The intense redox power, the ability to strip electrons, isn't always beneficial. It operates blindly based solely on thermodynamics.
Right. The bouncer can inadvertently throw the wrong guy out and cause a riot.
Yes, while it successfully sequesters lead and nickel, its strong oxidizing capability can interact disastrously with certain trace metals, particularly chromium.
What happens with chromium?
Well, if chromium thur, which is a relatively stable, benign form of the metal, is present in the soil, the intense electron-hungry nature of the manganese oxides can oxidize it.
Meaning it strips more electrons away.
Exactly, stripping away more electrons and forcing it to become chromium-6.
And chromium-6 is hexavalent chromium, the Aaron Brockovich chemical.
That's the one.
It is a highly toxic, highly mobile carcinogen that dissolves easily in groundwater.
Exactly. The manganese inadvertently transforms a safe, immobile mineral into a highly dangerous, mobile poison.
That's terrifying.
It highlights a crucial scientific truth. These minerals are not benevolent guardians of the forest. They are simply powerful chemical engines operating completely blindly based on the thermodynamic potential of their environment.
Right.
If the chemistry dictates making life-giving humus, they make humus. If the chemistry dictates making a deadly carcinogen, they make a carcinogen.
Okay, so we've seen how manganese reacts to oxygen and organic matter in the soil today, driving these massive planetary-scale biological reactions.
That's a busy element.
Very busy. Now, for the final act of this deep dive, we are going to wind the clock back, way, way back, over 2 billion years back.
We're going deep into the paleoclimatic record now.
Because there is a fundamental rule to everything we have discussed today. Manganese only forms these solid, complex oxides, these molecular hotels, in the presence of oxygen.
That is the key rule.
If there is no oxygen around, the manganese just dissolves into the water, remains soluble, and floats away invisibly.
Which presents geologists with an incredible tool. It means that ancient solid manganese deposits act as a literal physical receipt for the presence of oxygen in Earth's deep prehistoric past.
A receipt for oxygen.
Yes, if you find a rock made of solid manganese oxide, you know definitively that oxygen was present when that rock formed.
And to read the most spectacular receipt ever printed, the research takes us to the Republic of Gabon in West Africa.
Specifically, a geological formation known as the Francevilian Basin.
This is an immense, incredibly well-preserved sequence of unmetamorphosed sedimentary rocks resting on the ancient Archean basement crust. And these rocks date back roughly 2.1 billion years.
To properly set the stage for why this specific period is so critical, we have to look slightly further back to the Great Oxidation Event, or the GOE.
Right, which occurred around 2.3 billion years ago.
Before the GOE, Earth's atmosphere was a toxic smog of methane, ammonia, and carbon dioxide. There was virtually no free oxygen. But then cyanobacteria evolved in the shallow oceans.
And they started photosynthesizing.
They began producing oxygen as a waste product of photosynthesis, fundamentally altering the chemistry of the entire planet.
Earth essentially took its first breath.
Exactly. But the aftermath of the GOE was not a calm, stable transition. It was incredibly violent and dynamic.
What happened?
Following the initial oxygenation, Earth experienced something called the Lomagundi carbon isotope excursion.
The Lomagundi event.
Yes. This was a profound period lasting over 100 million years, characterized by massive, unprecedented burial of organic carbon.
Okay, we need to break that down because carbon isotope excursion sounds like a terribly boring geology conference. But it's actually the footprint of a dramatic planetary event.
It really is.
What does that mean physically?
It represents a profound shift in the mass balance of the planet's chemistry. Carbon comes in different atomic weights, or isotopes.
Like carbon-12 and carbon-13.
Exactly, those are the two most common. The lighter carbon-12 and the slightly heavier carbon-13. When biology, like those early cyanobacteria, photosynthesizes, it is lazy.
Lazy.
It prefers to pull the lighter, easier to process carbon-12 out of the atmosphere to build its cellular structures.
Makes sense. Biology likes the light stuff.
Now, normally, when that biology dies, it rots, and that carbon-12 is released right back into the system. But during the Lomagundi event, shifting tectonic plates created massive sedimentary basins.
It got trapped.
A staggering amount of this biological material died, sank to the bottom of these basins, and was rapidly buried by mud before it could decay. It locked all that biological carbon-12 deep in the Earth's crust, removing it from the active ocean atmosphere system.
Leaving the ocean heavily skewed. All the light carbon-12 is buried, so the water is suddenly full of the heavier isotope carbon-13.
Yes, and when inorganic minerals like carbonates precipitate out of that heavy ocean water to form limestone rocks, they record that heavy carbon-13 signature.
Oh, I see.
So when modern geologists find rock layers with wildly abnormally high carbon-13 levels, they know they're looking at an era of massive organic burial. And the Lomagundi event is the largest positive carbon isotope excursion in the entire 4.5 billion year history of Earth.
And here's the crucial part. Because burying all that organic carbon prevents it from rotting. And rotting is a process that consumes oxygen. Preventing the rot means the oxygen just builds up.
It has nowhere to go but up.
The oxygen levels in the atmosphere absolutely skyrocket.
Precisely. The Lomagundi event represents a massive runaway surge in atmospheric oxygen, likely pushing levels far higher than the initial Great Oxidation Event itself.
And we see the undeniable physical proof of this incredible oxygen high in the rocks of the Francevilian Basin in Gabon.
The receipt.
Yes, specifically in a rock layer called the FB1C subunit. Right in the middle of this geological sequence, researchers drilling into the basin found a massive, thick layer of sediment that is nearly 30% manganese by weight.
Finding a solid manganese oxide deposit of that magnitude from 2.1 billion years ago is the ultimate smoking gun for geochemists.
Why is it a smoking gun?
Because, as you established, manganese absolutely requires oxygen to precipitate from a liquid to a solid. The fact that a rock containing 30% manganese formed at the bottom of a deep marine basin proves unequivocally that the deep ocean at this specific time was heavily, thoroughly oxygenated.
The oxygen made it all the way down.
The oxygen produced by cyanobacteria at the surface had permeated all the way down to the seafloor.
But the researchers didn't just look at the black rock and call it a day. They wanted absolute proof. So they looked at the guests checking into the manganese hotel to prove the oxygen was there.
It did.
They looked at molybdenum isotopes.
This is where the detective work gets incredibly elegant. Molybdenum is a powerful proxy for tracking ancient oxygen.
Why molybdenum?
It is an element that is very well mixed throughout the global ocean. Under oxic conditions, when there is plenty of dissolved oxygen in the water, molybdenum gets scavenged from the seawater and trapped by precipitating manganese oxides.
It wanders off the beach and checks into the molecular hotel room.
Yes. But importantly, this physical trapping process creates an isotopic fractionation.
Okay, fractionation, meaning it splits them up.
Just like carbon, molybdenum has different weights. The manganese oxides selectively prefer to trap the lighter isotopes of molybdenum. Specifically, they measure the ratio of heavy molybdenum 98 to lighter molybdenum 95.
Okay.
When manganese pulls molybdenum out of the water, it shifts this ratio, it fractionates it, by about 3 per mil, or 3 parts per thousand.
Meaning the heavy Mo-98 gets left behind floating in the ocean water, and the lighter Mo-95 gets aggressively pulled into the solid rock.
Correct. So when researchers took samples of that 30% manganese layer in the FB1C subunit in Gabon and ran them through a mass spectrometer, they found surprisingly low, light molybdenum isotope numbers.
And that proves it.
These numbers perfectly mathematically match the exact chemical signature of molybdenum being scavenged by manganese oxides in a highly oxygenated ocean. It is a dual confirmation.
The hotel and the guest.
Exactly. The manganese hotel is there, and the molybdenum guest trapped inside it bears the exact isotopic fingerprint of an oxygen-rich world.
It is an incredible, irrefutable piece of deep-time detective work. The Earth was absolutely flooded with oxygen. Life was booming.
It was a very different planet.
Which it didn't last. The Lomagundi event ended, and the rocks just slightly higher up in the Gabon sequence, a sedimentary layer called the FD unit, which is dated to about 2.08 billion years ago, recorded an absolutely catastrophic planetary crash.
The crash is every bit as dramatic as the rise. When we analyze the FD unit, the carbon isotopes completely flip. We suddenly see highly depleted carbon-13 values.
Meaning all that light carbon-12 that got buried in the mud millions of years earlier is suddenly coming back into the system.
Yes. The geological force has shifted. Tectonic activity uplifted those vast, buried reservoirs of ancient organic carbon, pushing them above sea level and exposing them to the atmosphere.
And they started to rot.
They began to weather. And as that massive volume of ancient organic matter weathered and oxidized, it acted as a planetary-scale oxygen sink.
It just absorbed it all.
The decaying carbon violently sucked the free oxygen right out of the atmosphere.
Okay, I want to make sure I have this timeline perfectly straight, because it is wild.
Let's review it.
The Great Oxidation Event caused life to bloom. That life pumped out so much oxygen, it triggered the Lomagundi event, burying tons of carbon, preventing it from rotting, and pushing oxygen levels even higher.
Right.
The Earth is buzzing with oxygen. But eventually, the tectonic plates push all that buried dead carbon back up to the surface. And when it hits the air, it starts to rot. And the sheer volume of that rotting carbon sucks all the oxygen back out of the room.
That's exactly it.
It's like the Earth threw a massive millions of years long oxygen party and then spent the next 200 million years suffering a catastrophic, suffocating hangover.
That is a remarkably accurate, if highly colorful, summary of the geochemical feedback loop. The hangover was profound and deadly.
What happened to the ocean?
As the atmospheric oxygen plummeted, the deep oceans went anoxic again. They suffocated. But worse, they went toxic and eucynic.
Eucynic.
Meaning they became saturated with highly poisonous hydrogen sulfide produced by anaerobic bacteria thriving in the dark, oxygen-starved waters.
A completely poisonous ocean.
Yes. And we see the receipts for this euxinic ocean globally in the rock record. We see it in the molybdenum isotopes in the FD unit in Gabon, which violently shift away from the oxic signature we just talked about.
Where else?
We see it in specific iron speciation data. And most famously, we see it in the shunite deposits in Russia.
Shunite?
Which are essentially massive geological formations of fossilized oil generated by a dead, toxic, suffocating sea.
The oxygen levels crashed, and they stayed crashed for roughly 200 million years.
A very long hangover.
It wasn't until much, much later, around 1.89 billion years ago, that we see the formation of the shallow water banded iron formations, like the Gunflint Formation in North America. Iron dissolved in the ocean suddenly rusted and fell out of the water, indicating that oxygen was finally slowly starting to creep back into the shallow seas, long after the Lomagundi hangover began.
It demonstrates beautifully that the oxygenation of Earth was not a simple, steady upward staircase. It was a volatile, incredibly dynamic roller coaster driven by the ruthless feedback loops between biology, geology, and atmospheric chemistry.
And manganese is the chemical ledger that faithfully recorded the entire ride.
It truly is.
So what does this all mean for us? We started this journey by looking at a dull, knobby black rock sitting in the mud at the bottom of the ocean.
A blackened potato.
A blackened potato.
Yeah.
But it turns out manganese is so much more than a geological curiosity. It is a highly specific molecular hotel holding the exact metallic keys to our green energy future in its microscopic vacancies.
It's the bouncer and the bartender.
Right, the unseen biological engine turning dead autumn leaves into the fertile soil that feeds humanity. And it is a 2 billion-year-old time capsule that proves Earth's oxygen supply, the very air we breathe, is far more fragile and dynamic than we ever realized.
It is a single, unassuming element that forces us to reckon with deep time, the interconnectedness of planetary systems, and ultimately our own fleeting place within it.
Which brings me right back to the ocean floor and the proposed mining of those billions of tons of nodules.
The trillion-dollar question.
Think about those artificial manufactured replacement nodules. Scientists propose dropping into the Clarion-Clipperton zone to mitigate the ecological damage. If we unleash the tractors, strip mine the natural history of the ocean floor, vacuuming up 10 million-year-old geological pearls, and then replace them with our own synthetic concrete rocks just to trick the abyssal ecosystem into surviving, are we essentially terraforming our own planet?
It's a profound thought.
Millions of years from now, when the next intelligent species digs deep into the ocean crust and analyzes the rocks, will they find the magnificent chemical signature of the Great Oxidation Event? Or will they find the precise, terrifying moment that humanity decided to remodel the Earth to build a better battery? It's something to think about the next time you plug in your electric car.